So without further ado, Bill, take it away.
Thank you, Mayank. Let me just share my screen real quick. You guys can see this okay, right? Cool. Yeah, so my name is Bill. I'm a software engineer at LinkedIn, specifically the targeting team within the ads org. And this talk is sort of going to be about how do we use Pinot to approximate large multi-set cardinalities, specifically for our ads use case. Yeah, so this is going to be the game plan. I'm going to start by sort of introducing our use case, and then we'll go into how we are using Theta Sketch and Pinot to solve the problem. And then we'll end with some performance tuning that we did to achieve sort of the latency requirements that we needed. Cool. I'm going to start with the scenario. So if you put yourself in an advertiser's shoes and you're trying to, market or sell some product on LinkedIn, and you usually don't want to market to all of the LinkedIn's members because most people are not going to buy your thing. So you have some specific idea of who you want to show your ads to. And in this example, we're going to use that you want to market to people who live in the US or Canada and work at LinkedIn and knows some language, right? In this case, Java and C++. And the problem that we're trying to solve is how many people is that, right? So we want to tell our advertisers approximately how many people that you're targeting, just so they get a sense of their sort of audience pool. And here is a screenshot of our product. On the left side is where advertisers select who they want to target, right? So you can see that in this particular screenshot, the advertisers, this particular advertiser chose people who live in San Francisco Bay Area and people who have 10 to 12 years of experience in whatever field that they're in, and people who knows Java, right? And the problem that we're trying to, or the product that we're building is we want to display this number on the upper right? We want to say this is approximately 120,000 people on LinkedIn. And cool. Yeah, so this is sort of just a Venn diagram representation of our previous couple of slides. This is the same scenario, right? And the question we'll want to answer is how many people is in the middle? It's how many people is sort of the three question marks here, right? So I'm going to start with a couple of naive approaches. So the first approach here is what you can do is sort of take all possible combinations here, and what this represents is basically each row is sort of a you can think of each row as a member, right? So this row is like a member that has skill Python and Java, and this guy works for Slack, and he or she lives in sort of the US, right? And you'll have basically like a row for each member. And how do you get this count? How do you approximate this count, right? You will just do a simple filter and then just do a group by and sum, or a group by count, right? This is sort of the very first naive approach. And why this naive approach doesn't work, right? This actually generates an extremely large data set. The example that I gave before was using about 3 dimensions, right? It was location, skill, and something company, right? But you can sort of imagine a member on LinkedIn can have like a bunch of different attributes. So we have about 50 sort of attributes that we can intersect and perform diffs on. So this is sort of like an extremely large data set that we generate, and if we put this much data and we push this data into Pinot, this is actually taking sort of it could take hours, right? A super long time. And another thing is that this sort of grows with the number of members, is linear to the number of members that we have, right? And what's making it worse is that each column is multi-valued, because, for example, a member can have multiple skills, right? So it really blows up this data set, the size of this data set, which is why this naive approach one really, doesn't work out that well. Sort of another approach here, we can sort of take an inverse index, if you will, where the key is now the like the set identifier, right? So the key would be people who live in the US, and then you have like a bunch of a hash set of a bunch of member IDs. A key would be Canada, and then you have a bunch of member IDs, and so on and so forth. Right, and what you can do is sort of just perform union, intersection, and diff operations on the fly. And this set could also work if you have sort of, if the set size is manageable, when it's like 100, 1,000, maybe 10,000. But when we're at like sort of LinkedIn scale and we have hundreds of millions of members, this set really, this approach really doesn't work out that well either, right? So this is sort of a summary of what I just talked about, and this, the size of each row could get extremely large, right? If you have, a huge, a set with a huge cardinality like geo equals US, right? How many LinkedIn members are there in the US? This row can really grow to, megabytes, gigabytes, right? And when we're at query time, it'll be really slow because we have hundreds of millions of members in a set. So, yeah, so that was, again, this is all sort of very simplified. And, what if the set looks like this, right? If we're taking 5 dimensions, and you can see sort of how many unique little areas that we need to compute cardinalities for, right? And what if the set looks like this? So it could really get complicated when we have 50 available dimensions for our advertisers to choose from. Cool, yeah, so this is sort of the problem that we're trying to solve. And I'd like to sort of go into an overview of Theta Sketch and sort of how data sketching algorithms work in general. So Theta Sketch is a approximation, or like a probabilistic data structure, if you will. It's very similar to hyperlog-logs, both of which are used for count distinct queries, right? Both of these algorithms and data structures are used to approximate sort of a distinct count within a set or multi-set. The difference is Theta Sketch has more set operation supports, right? So Theta Sketch actually supports union, intersection, and diffs, but hyperlog-logs only support union. So in our particular use case, where we allow advertisers to sort of and, or, and do all sorts of different, complex Boolean expression breakdowns, hyperlog-logs really doesn't work out that well for us, but Theta Sketch sort of does what we need. And another sort of a minor difference is that hyperlog-logs, the serialized data structure, is a lot smaller and more compact than Theta Sketch. And but Theta Sketch sort of provides more functionalities, which is sort of what we need here. Cool. Yeah, so this is sort of a slide about the error of the estimation. So whenever we talk about estimation, there's usually an error. And Theta Sketch is sort of not any different, right? There is a probability distribution. And so if we look at this table on the right side, hope you guys can see my pointer, the left-hand side columns represent the size of the sketch, right? So as with a lot of different sketching algorithms that you might be familiar with, you can sort of tune how big a sketch is. And the bigger the sketch, the smaller the error. So, right, so you can see that the error margin sort of drops as you move down the table, but the sketch size goes up. So it's sort of like a trade-off game that you would have to play with for your particular data set if you do decide to use Theta Sketch. And the good thing about Theta Sketch is that the API actually supports you to query a range, right? So you can ask the Theta Sketch API saying, hey, if I want a 95% confidence interval, what would be the range of the approximation? And the API will give you like sort of 2 numbers saying that, hey, it's sort of between 100 and 300, for example. And realistically, it won't be a bell curve like this. It won't be as perfect of a bell curve as this, but you get the sort of idea. Cool. And the side I want to talk about sort of the error of the estimation is also very much data and query dependent. This is an example that I'd like to give. So for example, right, if you have a set with 1 billion items and then you want to approximate the intersection with a set with 1 item in it, right? So 1 billion union like 1. You know, don't be surprised that if the estimation gives you estimation of 0, right? In which case you will get 100% error. So, you know, this example is just to show that it's very much query dependent. And if your intersection that you're approximating is much, much, much smaller, orders of magnitude smaller than the cardinality of the 2 sets that you're intersecting, you tend to get like larger errors. But unions, on the other hand, is sort of less of a problem. Cool. I sort of do want to talk about different ways that we can sort of integrate with Theta Sketch. Sort of what we sort of did a proof of concept using a key value store. The key here is that we took the key of the key value store was a sort of a set identifier, right? So the key would be geo equals US, right, or geo equals Java, and the value of the value of the key value store was just a binary serialized sketch, and we sort of did this computation on the client side, you know, the performance wasn't really that great, which was why sort of Pinot comes into the picture. Pinot is sort of perfect for this sort of computation. On the client side, we had like super high GC overhead, super high memory, a lot of computation there, very low parallelism, which was sort of like a huge problem for us, which brings us to why Pinot is sort of perfect for our particular use case. Cool. Yeah. So this is sort of a example schema that you could use for if you want to use Theta Sketch and Pinot. Again, the key is that the set identifier, right? So for example, geo US, skill equals Java, you know, company equals Facebook, whatever, right? And the value is the binary serialized sketch. It's a sketch of the members that belongs to this particular set. And this is sort of the actual query, right? This is an example Theta Sketch query that you can use. You know, a select statement, and this is the aggregation function in the SQL. It's called distinct count Theta Sketch. And then this aggregation function actually takes a few different arguments. The first argument is the column name, right? This is the column that has the binary sketch. And then it takes this is sort of a parameter that you can tune. This is basically the sketch size. So you can tune how accurate you want your query to be at query time, right? At runtime, you can sort of tune the size. And the bigger this number, the slower the query is going to run, but you're going to get a more accurate result, right? And then the next set of arguments is the specific sets that you will want to estimate. So I've color coded these. These represent different sets. Okay, so these are, you know, geo US, Canada, skill Java, and company LinkedIn. This last argument, so the previous view is sort of like a variable argument sort of thing. You can provide a list of arguments there. And the last argument of this aggregation function is how do you want to aggregate these sets, right? So in this particular example, we want to union geo equals US and Canada, right? So because we want to target people who live in the US or Canada. And then the other ones are sort of intersected together because those are ands, right? So all of that, how do we want to merge these different sketches is sort of set by this last argument. And then the rest of the query should look very familiar to most of you, and it's just standard, you know, SQL query. So you specify a table name, and then you specify a filter where you would have to select all the rows here, right? So this is sort of an OR together. So you have to select all the rows here before you tell Pinot that how you want to union or intersect them. Okay. So that's sort of the anatomy of a Theta sketch query. Cool. Yeah. So this slide is sort of a breakdown of exactly how does Pinot handle this query. It's the same exact query as the previous slide. Okay. And it's a sort of the same query as the case study that we did a few slides ago. So after the broker receives this giant query, what it does is it actually sends all of these color-coded sets, these computations into a set of Pinot servers, and all of those servers would compute these sketches, or would get these sketches and compute them and send them back over to the broker. And then finally, this final argument, which tells the broker how do you want to merge these, right? How do you want to union intersect these? This guy is run on the broker. Okay, so sort of keep that in mind, and this is sort of gonna play a role in how we optimized our query runtimes in a later slide. Okay, so it's sort of very standard, like sort of MapReduce, like it sends a bunch of stuff out to the servers, and then the actual reduction step happens on the broker. Cool. The slide, and then I want to talk about sort of how we optimize the runtime of these queries on sort of the following slides. This, again, similar query, not exactly the same query as before. I've added more sort of sets in here, right? So now we're querying for people who live in the US or Canada and knows Java, C++, and work at LinkedIn, right? So if you remember that all of these arguments in the middle, the color-coded ones, they're run on each individual Pinot servers, which means if you have like a giant complex OR expression that you want to run, you're better off passing them over to the servers, which means instead of having dimension value US and dimension value Canada in separate arguments, you can actually have them in a single argument, in which case the single argument would get sent to one of the servers, and the servers would sort of do the union for you before passing it over to the broker for the final reduction step. So this is gave us a huge performance boost, about 70%. Yeah, so like there's a bunch of other optimizations that we've done along the way, and I'll talk about it in the following slide, but this sort of gave us the biggest sort of bang for our buck, right? Cool, yeah, so this is a slide of the, I guess, progress that we made over time. The initial few peaks, so you can sort of see, this is 4 seconds, right? 4,000 milliseconds, so this is 4 seconds. No optimizations and single threaded query, which means that we're sending a bunch of queries one at a time to this Pinot cluster. No optimizations, it was just 4 seconds, not great. And then we did some profiling. Huge thanks to my Yank. He helped a lot here. We performed a little bit. We did a little bit of sort of profiling, and we started doing various optimization here. I labeled each peak. So for this drop, it was we filtered out some empty sketches, right? That was taking up some CPU cycles there. And this particular drop, we sort of avoided redundant merges of empty sketches. And this last peak here, right? This peak was, now we're at about 500 milliseconds. This is the big one that I just talked about in the previous slide, where we're sending more work in parallel to the individual Pinot servers, and then and having the actual broker doing less work. And this peak we actually achieved with this average latency with 20 queries per second, whereas all of the previous peaks here were single threaded, right? So this is sort of like astronomically better than sort of the performance of the previous queries. Cool. Yeah, and this is a slide about what we were able to achieve using Theta Sketch on Pinot. We dropped our data size by 90%. Because we're now using sketches instead of like sort of exact counts, right? And we're also, due to the drop in data size, we're able to reduce the Pinot push size execution time by about 95%. So huge performance gains here. And some benchmark results here. So we're using some sketch size, right? This is sort of just a number. And we're able to achieve about a 500 millisecond latency at the 95th percentile with less than 20% errors at the 95th percentile. And this second table on the bottom here is just to show you how sketch size affects latency, right? If you drop the sketch size from, in this case, 20 to 12, our latency drops from 500 to 50 milliseconds. We didn't calculate the error margins here, but I would presume it's much larger than sort of 20%, right? So it's all very much data dependent. You're not, for whatever data set that you're using, you're not going to get this sort of the same results. So it's sort of very much dependent on the shape of your data. But for our particular use case, this is sort of the benchmark results. Cool. This is sort of last few slides. I just want to sort of summarize how Theta Sketch, how different queries affect error and latency. So I want to talk about errors first. Generally, intersections and diffs have higher errors than union. Okay. And intersections with sort of huge cardinality differences, right? That example that I gave where we're intersecting 1 billion with one item. Those sort of queries tend to have much larger errors than, you know, if you're intersecting 1 to 1,000 and like two sets with very similar cardinalities. And in terms of latency, this one's pretty straightforward, but I thought I would sort of outline it anyways. The more union, intersection, and diff operations that you're doing, the higher the latency. And obviously, the larger the sketch, right? If you remember, there's a sketch size parameter that you can use to tune your query. The larger the sketch, the higher the latency. Cool. Yeah. So this is just a conclusion slide. You know, if you have any sort of insights product where you want to perform a lot of you know, set count distinct cardinalities type of computation, specifically needing intersections and set diffs, Pinot plus Theta Sketch is sort of like a really good choice here. Cool. That's the last slide. Thank you very much.